Today I'm going to talk to you about polyanhydrides as a new Vitrimer material. So to start off, what are Vitrimers? They're a new class of polymeric materials. They have to be a covalently adaptable network, which means that they're a highly cross-linked network that can undergo a dynamic exchange to be reprocessed. So Vitrimers kind of bridge the gap between the current polymer classes, which are thermosets and thermoplastics. Thermosets are cross-linked polymers that have great thermomechanical stability, chemical resistance, and they can be applied to lightweight applications. And thermoplastics are typically linear or branch polymers that can be reprocessed or are malleable. So having a material that can bridge that gap, that have great thermomechanical stability as well as being reprocessable, is highly ideal. The covalent adaptable networks can be self-healing. They can undergo shape memory, and they are responsive, adaptive, and can be recycled. To be classified as a Vitrimer, you have to have reversible crosslinks that undergo an associative exchange, which means that the bond addition is occurring before the bonds are breaking. This helps maintain the crosslink density throughout the exchange process, which is in result will have a solvent resistance where it will maintain its cross-linking and will not dissolve in solvent. So the Vitrimer material that I'll be talking about today are polyanhydrides. We first discovered that polyanhydrides can undergo this dynamic covalent exchange when adding a small anhydride to a larger, higher molecular weight linear polyanhydride. So what you're seeing here is a linear anhydride made of PNA, pentanoic anhydride, with HGT or hexane dithiol. And we react these polymers at a 1-to-1 ratio to create a linear polyanhydride. And then we added a small anhydride molecule, or the PNA monomer itself. And what we were expecting is that these anhydrides were able to interact and break the larger linear polyanhydride into smaller polyanhydride polymers. And we mixed these two together under nitrogen to prevent degradation, and we heated up to 60 degrees C. And we monitor this exchange through GPC, or gel permeation chromatography. And what you can see is that right here at 20 milliliters retention volume, we have a high peak at first, and this is representative of the unreacted pentanoic anhydride. And as time goes on, you see that unreacted pentanoic anhydride peak disappearing as the polymer peak near the 15 milliliter range slowly starts to shift to higher retention volumes or lower molecular weights over time. This is showing that the larger polymers are now breaking into smaller polymer chains, which is what we expected. Now, one can say that, how do you know that degradation isn't occurring instead of this exchange? One, the fact that the unreacted PNA monomer is decreasing over time as the polymers are shifting to lower molecular weights. But we also wanted to do another study using GCMS. So we took two anhydride monomers, and we mixed them together in dichloromethane at 60 degrees C, similar to before, for 3 hours. And we looked at the mass spec of these materials as well. So what you're seeing down here at the bottom is the retention time for the gas chromatography. And you see after 3 hours that you have 3 peaks occurring, meaning that there's 3 separate molecules in this mixture. And we were able to look at the mass spec and break down the fragment mass to charge fragments for each of the materials. And for peak 1, it would be the methacrylic anhydrides that has a mass to charge ratio of 98 as well as 69. And peak 3 has a mass charge ratio of 100, 83, and 55. And the peak in the center has a combination of all of these, showing that, in fact, an asymmetric anhydride is forming. We wanted to take it further and do a kinetic study of this exchange. So we did a carbon-13 NMR, and we did so because we were able to monitor the shifts in the carbonyl peaks upon the formation of the asymmetric anhydride. So if you look at the pure MMA, you could see a peak around 163-ish, a little bit below that. And then for the PNA, it typically is around 168. And then as time goes on, you can see small peaks occurring right next to the main, the symmetric anhydride peaks. And this is representative of the asymmetric anhydride. Now, I want to state that I know there could be concern with using carbon NMR for a kinetic study, but I want to assure you that we're not comparing peak to peak in each of the integrations. We're comparing the integrations over time. So we're comparing the same carbonyl-carbon integration over time. And this allows us to look at the carbonyl integrations at different temperatures. In doing so, we see that at lower temperatures, it takes longer to reach an equilibrium compared to the higher temperature of 50 degrees C. And from this data, we're able to get the rates of degradation, or the rates of exchange, as well as the K equilibrium of each of the reactions at the different temperatures. So you can see that for the equilibriums, they're all roughly around or are close to unity, which is delta G equals 0. And that could be understood by the fact that the difference in the material before and after are relatively the same. So you're going from an anhydride to an anhydride, you don't have a dramatic change in the structure of the material. So that explains why the K equilibrium is around unity. And then we were also able to take the rates that we got from each of the temperatures and plot it as a Arrhenius equation to get an activation energy of 178 kilojoules per mole, which is relatively high. And we expected that because we weren't expecting an exchange to undergo so rapidly. But if you look at the carboxylic acid addition, so what we did was we took a carboxylic acid of one of the monomers, which is the pentanoic acid, and we added it into the exchange and monitored it over time. And you can see that at 35 degrees C, you have a rate that is 6.2, oh my goodness, 6.92 times 10 to the negative 7. Whereas when you add just 5 weight% of the pentanoic acid, you have an increase in the forward reaction of 2.09 times 10 to the negative 6, while the equilibrium does not change and it still is close to unity. So we are seeing a catalytic effect with the pentanoic acid addition, so we'll be studying that further. And then we did some studies with the dynamic covalent exchange in polymer materials. I want to say that if you want to see all of these different material compositions that we have done, please go to Rebecca Measham's presentation, because she went more into depth into all of the different types of compositions that we did. But I just wanted to prove to you that these polyanhydrides can be considered a Vitrimer material. So what you're seeing here is the PNA monomer that we've been studying with the HDT, and we add in a cross-linking material. So this PET-MP, it's a tetrathiol, and we add an initiator and undergo photo initiation. And we have these cross-linked materials which have our anhydrides that can undergo exchange. Now the material that I'm going to be focusing on is the 80-20, which is the least cross-link system. And the reason I'm focusing on this is because it has the highest rate of exchange. So I will be focusing on this because it's easier to do the different material processes with the quicker reacting or quicker exchanging material. So first, to prove that it is a Vitrimer, we wanted to do a solvent resistant test. So what you see here is the PNA HTT PET-MP with the 180-20. And we put this in a toluene at a ratio of 1 weight% of the polymer in the toluene. We chose toluene because it can go up to 110 degrees before boiling. And we typically do our exchanges at 90 degrees C. So we chose this toluene to do the reaction in, and we first did the solvent resistance at room temperature where typically no exchange is occurring. And we placed the polymer into the material and waited for 60 minutes and test the swelling of the material. We do have an increase. There was a swell of a 65% increase in mass and a 90% increase in volume. But the material did not dissolve, which is exactly what we're trying to prove, is that it's maintaining its cross-link density. And then we did the same polymer material with a 1 weight percent polymer and toluene at 90 degrees C, which is where we typically see exchange occurring. And you do see that you have a more of an increase in the mass and the volume. But overall, it is maintaining its cross-link density. Now, the exchange could be occurring, which could allow for more solvents to get in, but overall, the cross-link density is maintaining itself and it's not dissolving in any way. And then we did some self-healing tests on the same pentanoic anhydride HDT PETMP material. And we did this at 90 degrees C. So what you're seeing here is the pre-cut material. Then we took a razor and we sliced it in completely through the material, about halfway in its width. And then we monitored the material over 4 hours, and you can see that the cut itself begins to decrease until it completely disappears around 4 hours. We did some tensile testing with this material, which is basically clamping the material into a tensile machine, which will pull the material apart until it breaks. So what you're seeing is the blue lines are the original material that have been heat treated at 90 degrees C but have not been cut. And the red lines are the healed material that were pressed together after being notched, and they were healed for 4 hours at 90 degrees C. And then the black lines are the notched material, which you could see that there are variants in this DMA, or not DMA, the tensile results, but that is expected to occur because we're having different materials being placed in different locations, and you have to tighten each one. So there are variances just in mechanical and operational error. But overall, if you look at the summary at the bottom, you can see that the original and the healed material all has a Young's modulus, a peak stress, and a strain at break and tensile toughness, all within error of each other. And that goes to show that the healing process is occurring and the mechanical properties of the material before and after do turn out to be the same. And then we did a recycling test, which basically we took the material, completely chopped it up, and pressed it in a hot press at 90 degrees C with 5-ton pressure, which resulted in 76 megapascals of pressure to the material for 15 minutes. And we completely recycled that material. And we, in fact, got a better peak stress than the original, and that's due to the fact that we are able to undergo this exchange and we have a tighter density occurring because we have that pressure that is being applied. But overall, the material was able to be recycled. So in conclusion, the GPC data combined with the GCMS results prove that dynamic covalent exchange can occur. The carbon-13 NMR was used to monitor the kinetics of the dynamic covalent exchange, and it resulted in an activation energy of 178 kilojoules per mole. The carboxylic acid catalysis needs to be studied further, but it does prove to have a catalytic effect. The polyanhydride systems are solvent resistant and can successfully undergo self-healing as well as recycling. And the anhydride dynamic covalent exchange is an effective tool to heal the materials.